When you've completed this lesson, you should be able to simplify expressions with powers and roots and solve for a variable in an equation with powers and roots. Photonic technicians need to work with powers and roots quite a bit. For example, 6 to the 3 power, 2.7 to the 5 power, or with variables like x squared, or 2x plus 5 to the 7th power. Or you may have roots such as the square root of 2, or with variables the square root of x over 3, or cube roots such as the cube root of 6, or the cube root of an expression of an equation like 5z squared plus 3z minus 12. Sometimes you'll have a formula like a radiation intensity I as a function of the distance from a source. I is equal to I sub 0 over d squared. Or you may have a more complicated expression such as the threshold gain in a stable laser cavity, which is given as G sub A is equal to 1 divided by the square root of R sub 1, R sub 2 times L. Let's look at a typical scenario that a photonics technician may need to solve. A measure of the distance and time required to propagate light down an optical fiber is called the intermodal dispersion, tau sub I. And that's equal to L divided by 2 N1C times the numerical aperture squared. And the numerical aperture is square root of N1 squared minus N2 squared. And you're asked to find out what is the intermodal dispersion for a 1 kilometer fiber with the two values of N1 and N2 given there and using the speed of light. So we'll come back to that after we review some of the skills necessary to complete that problem. Powers is just repeated multiplication. So power notation is a shorthand way to write repeated multiplications. So you might recall the powers of 10 that we used in a previous module. For example, 10 squared is equal to 10 times 10, and 10 cubed is equal to 10 times 10 times 10. So we just repeated the multiplications of 10 based on those exponents. Well, similarly, we can have the expression 8 to the 4. That's a power. 4 is the exponent, and 8 is known as the base. The base is used as a factor exponent times. That is, 8 is multiplied by itself 4 times, or we can say that we have 4 factors of 8. A number or a variable with no power is the same as the first power. So, for example, 5 is equal to 5 to the 1 power, and 10 is equal to 10 to the 1 power. A is equal to A to the 1 power, and X is equal to X to the 1 power. So anytime that you see those variables by themselves, know that they really have a 1 as an exponent to them. That'll become important when you start to multiply and divide powers. A number raised to the 2 power, we say squared. So 6 squared or x squared. A number raised to the 3rd power is commonly said to be cubed. So we'll have 4 cubed or y cubed. And a number raised to the 4th power would be like 7 to the 4th, or we'll say z to the 4th power. Let's look at the example 1 that discusses breaking distance with the formula b is equal to r squared divided by 30f. B is the breaking distance, r is the initial speed, and f is the surface factor that we're driving on, and given by this table of values here. So given that a car is traveling at 55 miles per hour on dry asphalt, let's find the estimate of the car braking distance. Well, the solution is to substitute the values into the formula. So the units are already prepared in the driving surface factor to yield the braking distance in feet if we supply the initial speed in miles per hour. So if we put our speed of 55 miles per hour and our driving surface factor for the asphalt road is 0.85, and multiply it by 30 and evaluate it, and we'll end up with 120 feet as the braking distance. part B says that we have some skid marks on wet asphalt at an accident scene that measured 215 feet. So what would be the initial speed of the car that caused those skid marks if they were braking as hard as they could? Well, first we need to isolate R in the formula because we need to find what was the rate of the car. So we'll multiply both sides by 30F because R is divided by 30F. And the 30F on the right side will cancel, and on the left side we'll be left with R squared is equal to 30F times B. Take the square root of both sides so that we can get R by itself, and R squared is equal to R, and the square root of 30FB is on the right hand side. So that's our answer to the formula for R. Now we just need to substitute in the values into the formula. Remember, we're using F is equal to 0.65 for wet asphalt, so we have R is equal to 30 times 0.65 times 215, and the square root of all of that. So you'll evaluate that with your calculator and you'll end up with 65 miles per hour. Now, multiplying positive numbers always yields positive values. However, if we have negative numbers now, multiplying an even quantity of negative numbers will yield a positive value. So, for example, if we multiply negative 5 times negative 5, that equals negative 5 squared, we'll get 25, a positive number. But if we multiply an odd quantity of negative numbers, we will get a negative value. For example, if we have 3, 5, 7, 9 odd numbers of a factor that are negative, we'll have a negative number. So if we have minus 5 cubed, or negative 5 times negative 5 times negative 5, the result will be negative 125. So in general, we can summarize the results of our odd and even powers in this table. So we have an odd power and a positive base, we have a positive value. We have a negative base, we'll have a negative value. But then an even power, no matter what we have, positive or negative base, will have a positive value. You might want to jot this table down because it'll be helpful to remember. Now there's a trap that you'll have to watch out for when you're using your calculator. You know that 5 to the 4th is going to be positive 625, right? And negative 5 to the 4th will also be 625, positive 625. But try this with most calculators, negative 5 to the 4th power, and you'll get the answer of negative 625. Uh-oh, what happened? Well, you remember the please excuse my dear Aunt Sally? Well, the calculator knows that rule and follows that rule, so it first evaluates the exponents in the 5 to the 4th and then multiplies by negative 1. So the result will be negative 625. So not what you expected. So the moral of the story is know your calculator. Alright, so you've heard of square roots, right? The square root of 49 is the value when squared that yields 49. So we found out that 7 does that. 7 squared, sure enough, equals 49, so the square root of 49 equals 7. Similarly, the cube root function, the cube root of 125 is the value when cubed yields 125. So 5 cubed equals 125, and the cube root of 125 equals 5. So in general, we can say that the nth root of a number x, shown like this, is that value when raised to the nth power that yields the number x. So if we have r to the n equals x, then we'll say with confidence that the nth root of x equals r. Now, most calculators have a square root key, or an inverse function, used with the x key. So, for example, let's find the square root of 256. The solution is going to vary by the type of calculator that you have. So, with the TI-80 series of calculator, you'll take the second square root function that's on your key and enter in 256 and press enter. and you'll have your result. With an earlier model of TI 30 series, you will have to enter 256 first, and then go for the second square root function, and then press equals and get your result. And of course the answer is 16, and that will appear in either case. And you can check your answer, and you should do this to make sure that you're getting the right result that you expect. Remember, know your calculator by simply calculating 16 squared. Do you get 256? Alright, good. Now let's take a look at example 3, where we're given a square storeroom floor must provide 6,000 square feet of floor space, and we have to find the length of each side. Well, the solution is to start off with the formula for the area of a square, which we know is A is equal to S squared, where S is the side that we're looking for, right? So we're going to solve for S. To do that, we need to take the square root of both sides. Remember, in an earlier module, we talked about doing the same thing to both sides of an equation will yield a valid result. So we're going to take the square root of both sides, and knowing that the square root of S squared is going to give us S. And so we have S is equal to the square root of A. Next, we substitute for A the value, which is 6,000. We put that into our calculator and evaluate that, and the square root of 6,000 feet squared will separate, and we'll separate the units and the value, and the square root of 6,000 we can do with our calculator, and the square root of feet squared will be feet. So our answer is S is equal to 77.46 feet. Now, does that sound right? So to check it out, we're going to take our value for 77.46 and square it, and you get about 6,000 feet squared? Good. Cube roots now are a little bit different. You may not have used those very often, and they're a little bit harder to work with on your calculator. Recall that the cube root of 125 is the value, when cubed, that yields 125. Just like we did with squared, 5 cubed equals 125, and so the cube root of 125 equals 5. Most scientific calculators have a root key on them, like x root of y, or an inverse function that's used with the y to the x key. The undo operation for y to the x would be the x root of y. For example, let's find the cube root of 8. Let's see if we know how to do that. So it's going to vary by the type of calculator that you have, but again, we begin with a TI 80 series. We press the math button, and then you see the cube root function is on there, and then you enter the number 8, and then press enter. And the calculator will give you the result. On a TI 30 series of calculator, you would have to enter the value first, then press the second x root of y function, and then enter 3. And it says that you want the third root, and then press equals, and you'll get your result. And the answer 2 should appear in your display in either case. Now, you can check your answer by calculating 2 to the third power. Example 5 asks you to calculate the length of each side of a box that must hold 256 cubic inches of material. So it's a cube-shaped box. That gives us a clue that the formula for volume of a cube is V is equal to S cubed. Now we're looking for S, so we're going to have to use some algebra to solve for S. So we'll start with taking the cube root of both sides, remembering that the cube root will cancel the cube. So we'll be left with just S is equal to the cube root of V. We'll substitute in our value for V, 256 cubic inches, and we'll evaluate the cube root and the units separately. So the cube root of 256 and the cube root of the inches cubed gives us 6.35 inches. Now check your answer. If we take 6.35 and cube it, do we get about 256 inches cubed? Perfect. Now let's look at the solution to the opening scenario with those complicated expressions where we're asked for the intermodal dispersions using those two formulas, noting that NA will have to be inserted into the formula here. Let's substitute in the given values. So we have t is equal to 1,000 divided by 2 divided by 1.465 divided by 3 times 10 to the 8th meters per second, all multiplied by this expression for NA squared. Notice that the squares are going to cancel the square root for us. So that's going to be very nice because then we can just simply take that expression and stick it into the numerator without having to do the root anymore. Remember, please excuse my dear Aunt Sally because we're going to have to use that to evaluate this expression. So the result becomes 4.97 times 10 to the negative 8 seconds. More commonly, we'll be thinking of looking for nanoseconds, or 10 to the minus 9 seconds, so we might express this as 49.7 nanoseconds, or about 50 nanoseconds is the intermodal dispersion for this length of fiber. Okay, so let's go through a few practice exercises. Now, we won't go through every single one of them, but we'll answer just enough to give you the confidence to be able to answer the rest on your own. Starting off with exercise 1, we have the period of a pendulum is equal to t is equal to 2 pi the square root of L over g. So we're going to use g as 980 centimeters per second squared. What is the period t for a length of 25 centimeters? Well, we need to substitute the values in. So t is equal to 2 pi equals square root centimeters divided by 980 centimeters per second squared. And we'll handle the units separately that are under the square root also. So the centimeters will cancel and the per second squared will turn into just a second by itself. And the value of square root of 25.0 divided by 980 will have to be square root and multiply that by 2 pi. And the result should be 1.004 seconds, and we rounded that off. So a 25 centimeter pendulum has a period of slightly more than a second. Now, if we continued on, suppose the length was shortened to 24.9 centimeters. Would the period be closer to 1 second? Well, we'll substitute those values in and find out. So we substitute 24.9 centimeters in, and we'll handle the units separately as we did before, evaluate the expression under the square root, and multiply by 2 pi, and we have t is equal to 1.002 seconds. So sure enough, shortening the pendulum by 1/10 of a centimeter brings the period a little bit closer to 1.00 seconds. So here's an extra challenge for you. We can just solve the formula for L and find the length of the period that is exactly 1 second or exactly 2 seconds. But I'll let you go ahead and do that on your own using the algebra skills that you've developed in the past couple of modules. Now, exercise 2 gives us a problem of finding the monthly payment for financing a $2,600 car over 24 months using this formula here. So R is equal to P times I over 1 minus 1 plus I to the negative n power. Well, we can start off by substituting the values in to find the monthly payment. So substitute in 2,600 times 0.01 for the interest. 1% is the same as 0.01. And also in the numerator, 1 plus 0.01 to the negative 24, since we want 24 months. We need to evaluate this with all the decimal places that we can get in our calculator because it's a very small little number. So we're going to start by doing the 1 plus 0.01 to the negative 24. We end up with 0.787566 and we evaluate that expression in parentheses and multiply by 2,600. To do that with a scientific calculator, with a TI-80 series, for example, we'll multiply 2,600 times 0.01 divided by, now we need the denominator, and I'm going to do the math in my head for what's in the parentheses and call that 1 plus 0.01 is really 1.01, and we need to raise that to the negative 24 power. So notice we're using the power function and the negative operation function, and close that all with parentheses and press enter. On a TI-30 series, it's a little bit different. We'll use 1.01 in our head and when we add those two numbers, and then we use the y to the x key. and tell what we want the x to be, and we want it to be 24, and we change the sign to negative, and we press equal. So in both cases, we should get $122.39 per month. Exercise 5 gives us a formula for calculating the energy from a black object that's radiating, total energy R, and the temperature T in Celsius. What's the total energy radiating from a 300 degrees Celsius object? Well, we substitute in the values for T and evaluate. So we'll put the 300 into the formula, and now we have to add the 300 and the 273 and take it to the fourth power. So here's the value to the fourth power, and here are the units all pulled out. We notice that we have c to the fourth, and c to the fourth will cancel. And then we have the number in scientific notation times 573 raised to the fourth power will be a really big number. Using a scientific calculator, again, we've got the scientific notation of 5.67 to the EE negative 12 times 573 raised to the fourth power, and then press the enter sign. For a TI 30 series, similarly, we would have to put the exponent in the scientific notation times 573 y to the x to the 4. And the result will be R is equal to 0.661, and we're left with just watts per squared centimeters as the units. Second part of exercise 5 asks us to do the same thing with a 37 degrees Celsius object. So again, we'll go ahead and substitute the values in. 37C goes right where the T used to be, and that'll all be raised to the fourth power, so we'll have 310 raised to the fourth power. And again, the Celsius units will cancel out nicely. And using a scientific calculator as before, negative 12 on the exponent, not a subtraction 12, and a power raised to the fourth. And on a TI 30 series of calculator, similarly, using the y to the x key, will give us R is equal to 0.052 watts per centimeter squared. Much less energy than the other one. Stirling's formula is a popular way to approximate the factorial functions for very large numbers. You'll notice that n factorial is approximated by the square root of 2 pi n times n over e raised to the n power. Now, that's a pretty complicated formula, but it's a lot easier than calculating n factorial with a large number like 30. Substitute n into the formula. So 30 factorial is approximately equal to the square root of 2 pi 30 times 30 over 2.71828 raised to the 30th power. When you use your calculator, make sure that you use all the digits that you can use to get, because if you just use 2.718, for example, your answer is going to be way, way off when you raise something to the 30th power. So you'll have a number something like this. So the square root of 2 pi 30 is about 13.729 in your calculator, and you'll keep all of those digits. And 30 divided by 2.71828, etc. is about 11.036, and again, you'll keep all of those digits and raise it to the 30th power. And with a scientific calculator, with a TI 80 series of calculators, you'll do something like this, using the power function to the 30th power, like before. And similarly, with a TI 30 series of calculators, you'll use the second e to the x to get your e here and the y to the x function to get 30 power. And the result should be about 2.6452 times 10 to the 32 power. Alright, so I hope that you've got your confidence built up by going through this module with me and working some of these practice exercises with me so that you can work out those other practice exercises by yourself. See you again next time.